We're going to continue our study of combining two functions to create a more complex function. We've talked about adding and subtracting two functions. Here I have x squared added to sine x to create a new function that looks like a slightly changed parabola. This video we want to talk about multiplying two functions. So here's what I get when I multiply x squared by sine x. And the order of multiplication is not going to change what we get. Let's look at division though. I'm going to take here x squared divided by sine x. And then I'm going to do it the other way around, sine x divided by x squared. I can see that I do get a different graph. And some quite complex looking graphs as well. So let's just go back to basics with two simple functions. I've got two lines here, and what I'm going to do with these two lines, I've got them graphed already. I'm going to create f times g of x. Now that notation just means f of x times g of x, which in this case would be x plus 1 times negative 2x plus 2. And I think I can see that if I multiply this out, I'm going to get a quadratic, so I expect to get a parabola. Just in terms of domain, remember that the domain of my final graph, when I add, subtract, or multiply, is the overlap of the two original graphs. And so my domain on my lines we know is all reals for both. And so the domain on my final graph will be the same, as we would expect with a parabola. Now range is always more complicated to figure out, and we can figure the range out from our graph at the end and our table. The other thing I just want to say is that when you combine two functions, especially when you get into multiplying and dividing two functions together, it's hard to predict often what the new graph is going to look like. In this case, we know it's a parabola, but in many cases, you can't visualize or predict in advance what it's going to look like. Alright, so let's find some points for our new graph. And remember, those will come about just by multiplying the y values of the original graphs. So for example, if I were to put negative 3 into my function, I can see from that that the new y value will be the y value of the original with negative 3 plugged in times the other function with negative 3 plugged in. In other words, negative 2 times 8, negative 16, and so on. Multiplying the y coordinates to get the new y coordinate of the new graph. By the way, you don't necessarily need a table to multiply the y values. You could just go point by point on your graphs if they're graphed accurately. For example, if I was at x equals 0, and I can see a y value here of 1 on one graph and 2 on the other. So if I multiply those two, I know that the new y value is 2. So I just plot it. Alright, so I'm plotting all the points x comma h of x. Negative 2, 6 is way down here. Negative 1, 0 is there. 0, 2, 1, 0, 2, 6. I can actually see the symmetry in the table. The vertex is in a nice location. It's at 0, 2, and so I know my graph is going to look like this. And I can see that my range for my new function, the range is y values less than or equal to 2. Alright, here's another question. We want to find the product of these two functions, f times g. So algebraically that's easy enough to do. It's just f of x times g of x, which is going to create something new. I have no idea what this shape's going to look like unless I build a table or look at the graph. But I'm not asked to do that, I'm just asked to find the domain and the range. The domain, remember, is the overlap of the two functions. So on the parabola, the domain for this would be all reals. On this radical function, the radicand has to be positive, and that will happen if x is greater than or equal to 2/3. and therefore the overlap of those two means that the domain on my new function is x is greater than or equal to 2/3. The range is always harder to figure out. Let's see if we can reason it out. If I put these values of x into my function, if I put 2/3 in, I know that's going to result in 0 there and something more than 0 here, but I know that 0 times anything is 0. And I also know that the outputs for these two individual pieces is more than 0, so I can see, I think, that my range is going to be greater than or equal to 0. Okay, again, I stress it's not always so simple to figure out a range like that. Let's take a look at what this looks like on the calculator. Original function 1, original function 2, and my new function from 0 going up. In my table I can see what's going on a little bit better. You can see that the y values are getting large on the new function very quickly. We can also combine functions by dividing. And again, the domain will be the overlap of the two, but we also need to consider the fact that the denominator function cannot be 0. Alright, so let's take a look at this. We have f of x divided by g of x. So h of x will be x plus 2 divided by x squared plus 9x plus 14. And f of x is a line, so we know that the domain is all reals. G of x is a parabola, so we know the domain is all reals. So the domain of my new function will be the overlap of that, all reals, with the exception that the denominator can't be 0. So I can analyze that just by factoring and that's actually going to reduce to 1 over x plus 7. But remember, our restrictions come in before we reduce, so x can't be -7 or -2. So there's our two functions, and we want the division of those two. So here's f of x, our line, g of x, our parabola, and now h of x, which is f divided by g. We're getting something more complex looking, which is often what happens. And so let's just look carefully and interpret what the calculator is giving us, because what it's giving us can be misleading. So first of all, the points we're really interested in is -7 and -2, because we know the domain doesn't exist there. At -7, if you trace towards -7 from both sides on the final function, we're going to see that there's a vertical asymptote at -7. The y values are getting larger and larger from this side, indicating a vertical asymptote. And on the other side, they're getting really, really small if you keep tracing lower and lower. So that explains what's happening at -7, a vertical asymptote. What's happening at -2? Let's trace to -2 on the block graph, and we can see that there's no point. So right here, -2, I'm just going to turn the other two graphs off because they're just distracting at the moment. There actually is no y value at -2 because the graph, because when I put it in, it's undefined. Okay, remember, it's not putting -2 in here, it's putting -2 in the original function that makes it undefined. So in terms of the graph, if I were to graph this on paper, at -7 I have a vertical asymptote, and at x equals -2 there's a gap in the graph, which we're just going to show as a whole. And then the rest of the graph looks like this. Now in terms of what's going on over here to the right, if I trace that on and on and on, you're going to see the y values are getting closer and closer to 0, which is implying that we have a horizontal asymptote on the x-axis. So the graph's going over like that, closer and closer to the y-axis. and the same thing is happening on the other side. Okay. Now, I've talked about all that because I have to look at all those things to determine the range of the final function. The range is all values of y except 0 and the y value where x is negative 2, if it could be. Now, remember I said you got to put the negative 2 back into the original function before you simplify. If you put the negative 2 into the reduced form, you're going to get the y value that's being left out. In other words, y can't be 1/5. Domain, range. You can see how the range is more complex to figure out. So let's take the same function now and let's do the quotient of the two functions in the other order. G of x divided by f of x. And this is going to produce a different output. My domain, I can see, is that x can't be negative 2. Again, I can factor the top and reduce this function. And in this case, it reduces to a linear function. But it's a linear function with this restriction, remember, that x can't be negative 2. And if x could be negative 2 here, y would have been 5. So y is not going to be able to be 5. That's going to be part of my range. This is a linear function. Let's just see how this all shows up on the calculator. So I'm just going to change y3 to y2 divided by y1. As expected, there's my line with a y-intercept of 7 and a slope of 1. And at negative 2, there is no point on the graph. So if I was graphing this on paper, I'd have a y value of 7. The x-intercept would be negative 7, if you calculate it. And when x is negative 2, there would be no point at 5. So the graph looks something like this in actuality. You'll notice you don't see the gap on the graph, at least usually you don't. Sometimes, if your window dimensions are just a certain way, you will. But we know there's no point because there's no y value. It's telling us that right there. And we know that because when you plug negative 2 in, your denominator is 0.